Oh man, now I'm not overselling it when I say this is one of the coolest things you are going to ever study in calculus, or in my opinion, in math in general. We're going to jump into the chapter that is all about Taylor polynomials and power series. A lot on that. We're going to start in this lesson, in this particular video, with Taylor polynomials and what they are, and they are beautiful. Let's go. So basically, our goal is that we want to create polynomials, right? Those nice things, like a polynomial could be something like x squared plus x plus 1, right? Something really nice where you've got x to the power of something, another x. We could have coefficients, but it's nice and simple and sweet. We want to create those things that approximate functions that have no business being polynomials, like sine of x, cosine of x, e to the x, the natural log of x, the tangent of x, and so many other functions that we never thought were polynomials. Well, we can get polynomials to approximate the values that these functions give out and actually approximate them to as much accuracy as we want. It's so rad. So let's dive. It says that we're going to start by first making what is known as a fifth degree Taylor polynomial approximation for sine x. That means that we're going to go out to x to the fifth, or x to the 5, or a quintic polynomial centered about x equals 0. More on that in a little bit. For sine x. So if you ever wondered how these calculators, or any calculator for that matter, calculates sine of x, it's got a polynomial programmed inside of it. Isn't that cool? It's not about the triangles, it's about algebra. So to accomplish what we want to do, we need the polynomial we're making, our approximation, to have all its derivatives equal to all the derivatives of the function that we're approximating, in this case of sine. So that's what I call the true function, at x equals 0. That's where we're centered about it. So that means that f of 0, the function sine of x, must equal p of 0, the polynomial at 0. That means that the first derivative of this polynomial, when you plug 0 in, has to equal the first derivative of sine when you plug 0 in. The second derivative of the polynomial that we're going to make needs to equal the second derivative of sine when you plug 0 into both of those. And that's so that if we're building a polynomial that predicts sine as well as it can, all of the derivatives and the rate at which the polynomial is changing needs to equal to the rates of the sine function where we're starting our approximation. Otherwise, we already start out with bad error. It's very cool. And we'll go over why this makes a lot of sense as we go through this, and you'll see the pictures too to support it. So we're going to let our Taylor polynomial be p of x. I've seen some books, as well as the BC exam, write it as t of x. Doesn't matter. P of x, t of x, either way, completely up to you. And f of x, the true function that we're approximating, is going to be sine of x. Then, here's what we need to know based on that last statement, that the polynomial evaluated at 0, where we're centering our approximation, has to equal sine of 0, or f of 0. P prime of 0, the derivative of the polynomial we're going to build, will equal to the first derivative of the true function, sine of x, at 0. The second derivative of the polynomial at 0 needs to equal the second derivative of sine of x at 0. The third derivative of the polynomial needs to equal the third derivative of the true function at 0. The fourth derivative, and you get the point. Now we write fourth derivative. It's kind of interesting if you've never seen it before, with the parentheses and then the number 4. So we don't need to keep doing tick marks. So we're actually going to need lots of derivatives with this stuff. The fifth derivative equals the fifth derivative, and so on and so forth until we get down to any number derivative that we want. That's going to need to equal to that nth derivative where we're approximating. And think of an approximation when I say centered about x equals 0 or approximated about x equals 0. That's like where you're lining up your tangent line when you did a tangent line approximation at x equals 0. So how do we end up accomplishing a Taylor polynomial? What is it that makes it so that we get our polynomial to be equal to the derivatives of the true function we're approximating at every value? Well, I'm going to go over why the term that I'm about to write down works in a later video, but for right now, we're just going to use it and get down the process first. It's wicked cool. So the general term of any Taylor polynomial is f to the nth derivative at wherever you're centering the function. So that c value could be 0, could be 1, could be -1, whatever it is. So that's where we're centered about x equals c, and I'll put that here, centered about, or at, or approximated at x equals c. And that's going to be all over n factorial, interesting, times x minus c to the nth power. That is the general term of your Taylor polynomial. And we'll see how to use that shortly. For right now, you may be like, what the heck is this thing? It's not as bad as it looks. So in general, any Taylor polynomial about x equals 0, which by the way, if you're centered about x equals 0 and it's a Taylor polynomial, we can also call that a Maclaurin polynomial or Maclaurin series, just like it could be a Taylor series as well. So if you're centered about x equals 0, you might also hear the word Maclaurin. I like to call it Mac Dog. It's pretty sweet. So if we expand this whole thing out using these terms, we'd have f to the 0th derivative. That'd be basically f of 0. So that would be f of 0 times, and then it's got x minus c to the 0th, which would just be 1, all over 0 factorial. Well, that would be 1. And then you have plus. Now I have f to the 1st derivative, plugging in 1 here, of 0. Remember, c is 0 here, all over 1 factorial. I'll put the 1 factorial there just to be consistent, times x minus 0, which would be x to the 1st, plus. And you'll see that the derivative here lines up with the power here and with the factorial down there, which is really nice. So f to the 2nd derivative of 0, all over, it matches up here. 2 factorial, 2nd derivative, and then 2nd power, plus f triple prime of 0, all over 3 factorial times x to the 3rd, plus, and you get the idea, right? It keeps on going and going and going. And then we write out the nth term. So you see how this has a lot to do with the series we studied in the last chapter. So that's the nth derivative, evaluated in this case at 0, all over the n factorial, whatever that value is, times x to the n. So n, 3, 3, 3, 2, 2, 2. Just a nice way to memorize it, not necessarily to understand what's going on or why it's happening, more on what and why in a little bit. In general, any Taylor polynomial about x equals c, so this is just if we're not just centered at 0, but at any value c, so that'd be f of c plus f prime of c, all over first, but this is going to be x minus c, because in this case, it's like you're shifting the polynomial left or right. And then we've got plus f double prime at the value we're approximating, over 2 factorial times x minus c squared, plus f triple prime of c, all over 3 factorial times, it's beautiful, x minus c cubed, plus dot, 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 and then our nth term, which would be this term right here, f to the nth derivative of c. I'm going to have to curve this up a little bit. All over n factorial. That's it. Not so bad at all, except it looks nasty, right? It's scary, but it's a polynomial. These are all coefficients. The non-x terms, these things, believe it or not, are coefficients. You'll see that it's not as ugly as you might first believe. You should understand this pattern and then be able to expand it out in your class. Then you'll be in good shape. I would practice by just expanding this out a few times and seeing the pattern, that the factorial value matches with the derivative value and with the degree that you have here, and that if you have something other than x equals 0, it'd be x minus whatever that number is. Though, this also works if you plug in 0 for c. All right, let's keep going. High fives. We're learning Taylor. Right, the 5th degree. Taylor polynomial approximation for sine x centered about x equals 0. So now what we're going to transition into is we're going to actually build a polynomial that will give us an approximation for the values we get out when we plug sine of x. All right, so let's see. What I like to do to organize this is I always expand out whatever I'm trying to find out to the degree that I want. So I've done that already because I didn't want you to have to watch me write it all out. We use the typical Taylor series or Maclaurin series expansion, just like I went over in that last slide. And I'd like for you again to practice that kind of expansion again and again. You get really good at it. Now, all I'm going to do is write up what I call the bank. That's where I take all the derivatives out to the 5th derivative in this case, or to the derivative of the degree that I need. And then I plug in the c value that I want. In this case, c is equal to 0. So I'll show you what I do here. So f of x is equal to sine x. And then f prime of x is just the derivative of sine, which is cosine of x. F double prime of x. I'm organizing myself so I can just pull from this information and then put it all into this template. It's literally plug and chug. That's equal to minus sine x. F triple prime of x is equal to minus cosine x. We need the fourth derivative, of course. The fourth derivative, with a giant parentheses there for whatever reason, of x is equal to positive sine of x. And then the fifth derivative is where we'll stop, because as we see, that's our fifth degree term, is equal to cosine x. Okay, now what we're going to do is we're going to plug values into 0 into these functions right here. So f of 0 is equal to sine of 0, which is 0. F prime of 0 is cosine of 0, right here, which is 1. F double prime of 0, interesting, negative sine of 0 is 0. F triple prime of 0 minus cosine of 0 is minus 1. F quadruple prime of 0, bet you didn't think you need quadruple and quintic primes, huh? That's 0, because sine of 0 is 0. And then F quintic prime, fifth prime, the fifth derivative of sine, is equal to cosine at 0 is 1. So yes, some of the terms end up zeroing out. That's not typical in a Taylor or Maclaurin series, but it does happen in sine and cosine Maclaurin series only. It's kind of interesting. So all we're going to do now is plug in what we got. So a lot of people will write this polynomial as p sub 5 of x. That indicates the order of the polynomial that we're at. It's sometimes referred to as the fifth order or fifth degree Taylor polynomial. So f of 0 is 0, plus f prime of 0 is 1. I'm just going to show you those numbers plugged in and then simplify it on the next line, plus f double prime of 0 is 0. So a lot of this is going to cancel out. Plus f triple prime is 0. I'm just plugging in what I got. That's the advantage here of organizing everything into a nice information bank. It makes life easier. Plus f quadruple prime is going to be 0. Oh, nice. Plus, and then f to the fifth derivative at 0 is 1 times x to the fifth over 5 factorial. And this simplifies down to, well, the 0 is gone. We'll get x over 1 factorial is just x. That goes to 0. That's plus a minus. So it's minus x cubed over 3 factorial plus 0. 0 times the number 0. Plus x to the fifth over 5 factorial. A really neat pattern here. And you might notice that it's a pattern of alternating signs. The next one, you might be able to predict what's coming up next. It would end up being minus x to the 7th over 7 factorial, plus x to the 9th over 9 factorial, but we just wanted the 5th degree. So that's it. What that means is this is an approximation of sine of x centered about x equals 0. So now what I'm going to do is I'm going to show you what we just did step by step when we plugged in and got this term, then when we got this term, and then when we got that term. We want to see graphically what was going down. Very cool. So graphically, here's what was happening. So we started out with p sub 1 of x equals x. And again, I'll go back to the polynomial. That was just this part. P sub 1 would be the first degree polynomial only. And you've seen that before. That's a tangent line approximation. So I asked the question, have we made this kind of approximation before? Yes. That's a tangent line. You'll notice we're centered about x equals 0. This is what I mean by centered about, or a Taylor polynomial or Maclaurin series about a value. That's like your point of tangency, literally. It's where all the derivatives are going to be equivalent. In this case, it's just the slope of the line is equal to the slope of the curve at that point, and the y value of the curve and the y value of our approximation line is equal. So we could use that to approximate values on here's sine of x. So what does it mean to write a polynomial about 0? Like I said, it's like your point of tangency. All right, now what happens when we got our next term? We end up with x minus x cubed over 3 factorial. So you want to start to visualize this as if you're building something, getting more and more accurate. So here's your point of tangency. And this is almost like you have a tangent cubic polynomial. It's the way that I like to look at it. And notice that what's happening here, oh my goodness, it's starting to fit the curve nicely. Whereas our tangent line in this slide here just kind of went off, right? In both directions, it never curved back down. The cubic function is starting to bend nicely. You see that the concavities agree because our second derivatives agreed. Our third derivatives agree to this point of tangency. So we'd expect the immediate concavities and the rate of the concavity to be changing like sine of x does. But then this kind of diverges off on its own, the approximation function, p sub 3, that polynomial, and no longer matches sine. So when we get a 5th degree, we get a little bit more accurate. We get the rate of the rate of the rate of concavity. Oh my goodness, the fifth derivative to agree here, which gets more accuracy further along. You see that now we're not bending and going down, we're bending and then coming back up, so that these rates here and here are starting to agree. That was better than in this graph there. I think that's so wicked cool. So again, this is like a tangent quintic function. So quintic polynomial. And as we see, the further that we get away from the center where we're approximating everything, the worse off our approximation will be. But man, that's pretty darn close right there. All right, so that's the graphical representation of it. And a couple questions then based on that. We're going to put all this together really nicely. How could we increase the accuracy of our polynomial to fit f equals sine x even better than before? Well, let's think about this. We got to the fifth degree and everything got pretty close. Everything in calculus seems to be about going towards infinity. As n goes to infinity, meaning the number of degrees of the polynomial gets higher and higher and higher, sine of x is going to end up equaling out to, well, an infinitely long polynomial. We call that a Taylor series, an infinite series, or a Taylor, or a Maclaurin series in this case. So that would be x, we already saw this, minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus, and then it keeps going with this pattern, alternating signs, and then going up by an odd power every single time, and so on and so forth. So the general term, this one's a little tough to see, but you've got -1 to the n. N is starting in this case at 0. X to the 2n plus 1. That gives you odd numbers. Started at 0, you'd end up with 1. You plug in 1, you get 3. You plug in 2, you get 5. And you alternate the signs with this. All over, we have the same exact factorial as we do this exponent. So it'd be 2n plus 1 factorial. So again, this would be a Taylor series. As n goes to infinity, sine of x will equal to this. That's beautiful. Oh, it's awesome. So I drew out another graph for you. We're almost done here. I drew out another graph for you, and what it shows is what happens when we expand the Taylor polynomial just to 51 terms. Never mind to infinity, 51 is very small. So if we go out to 51 terms, that would be out to, I guess, the 100, first power is what we'd be out to? Or 100, 100 first power. Oh my goodness. Notice that from -10 pi to 10 pi, the curve fits sine of x almost perfectly. So you'll see here, this is the true value of sine of x. And this right here, that's like p sub 51. Or I guess it'd be p sub 51 of x. Oh, 51 terms. So 51 terms wouldn't be p sub 51, sorry. It'd be p sub 101, because you'd have 51 odd numbers. Oh my goodness. So what we notice is it eventually does end up, the approximation function will diverge. It'll go away, but it's going to fit sine of x perfectly. And so as n gets even bigger and bigger and bigger, it's going to wrap back around until it fits it perfectly all the way out to infinity. It's beautiful. So last but not least in this video, we can't get out of here without actually using the polynomial that we found to approximate sine of x at pi over 4. So we understand things algebraically, how to construct it. We understand it graphically, what this polynomial looks like and does. But now the goal is to understand how to use it numerically. So sine of pi over 4, we know what the true value is. This is the neat part. We're going to use sine of x, which is approximately, remember we called it p sub 5 of x, the 5th degree Taylor polynomial. And that's equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So it's just like a tangent line approximation, except it's like a quintic curve approximation. We would plug pi over 4 into a tangent line to approximate it. So in this case, we're going to plug pi over 4 into our polynomial. So sine of pi over 4 is approximately p sub 5 of pi over 4, and that's equal to pi over 4 minus pi over 4 cubed plus pi over 4 to the 5th. Now I'm going to pause for a second and find that as a decimal in my calculator. Oh, and I got this number, and you might be like, well, that's not that significant. What's this all about? So when I plug this into my calculator, I get 0.707143, and it keeps on going and going and going. Now, In terms of the number that we get for the true value, what's sine of pi over 4? Well, we know that that's equal to root 2 over 2, which is approximately 0.70706. Interesting. So hang on a second. We matched here, 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 here. It wasn't until this is tenths, hundredths, thousandths, 10,000ths, 100,000ths place that we're off by at pi over 4. And that's only to the 5th degree as an approximation. That's pretty good. Your calculator, it's kind of interesting, gives only an approximation for sine as well, but it goes out to many more degrees than this is. Now, what is the maximum error of our approximation? Meaning, what is the true value of this? Now, we know the exact value. We know it's root 2 over 2 because it's a nice value I picked here for sine. But what's the maximum error of our approximation? Notice that this is an alternating series. So since it's an alternating series with terms that decrease in absolute value to 0, these will decrease in absolute value to 0, we end up with the first ignored term, which would be the absolute value of minus pi all over 4, that raised to the 7th power. That right there would be the maximum error that we have. I'm going to calculate in the calculator to tell you the maximum amount that our approximation was off by. Okay, so the decimal approximation we get from our calculator is roughly 0.184, which means that's the most that this polynomial is off by when approximating pi over 4 of the true value of what sine of pi over 4 is. It's going to be probably less error than this, and if you wanted even less error, go out to x to the 7th, then go out to x to the 9th. Break this thing out as far as you want to get as little error as you need. Oh, it's beautiful. That's it. A ton on the Taylor polynomial, how to build it, what it looks like, and how to use it. I'll see you in the next video. We'll do a little more practice with it, and we'll learn some of the common types of Taylor series, Maclaurin series that you'll see. Until then, this was awesome. Peace.